Hi everyone, I hope you're okay, and I hope that the videos will keep uploading and helping you out. This is video number 9, whereby I'm tackling questions on rates of reactions, and please do expect a total number of 11 questions, and all of these questions are extracted from past exam question papers, and it's very important for you guys to know how to tackle such questions. So please do share the video to your peers, so that they may have the same edge as you. Okay, we are told that two experiments are carried out to investigate one of the factors that affects reaction rate between magnesium and dilute hydrochloric acid. The balanced equation below represents the reaction that takes place. We have magnesium as products. No, rather, magnesium and hydrochloric acid are both our reactants. And then for products, we simply have magnesium chloride as well as hydrogen gas. And then we are told that in experiment 1, a certain mass of magnesium ribbon reacts with excess dilute hydrochloric acid. And in experiment 2, magnesium powder of the same mass as the magnesium ribbon reacts with the same volume of excess dilute hydrochloric acid. The concentration of the acid is the same in both experiments. Okay, and then we are told that the apparatus below is used for this investigation. Okay, we have our conical flask, and obviously inside the conical flask rather, that's where the reaction take place. Now we have both our reactants, which is magnesium as well as hydrochloric acid, and then obviously inside we will have our products that are formed. Are you together? And secondly, we have our cottonwool over there. Né? The cottonwool prevents the hydrogen gas from escaping the reaction vessel. Are you together? So that's why inside over here we simply have the gas bubbles, just to show that just to show that the hydrogen gas did not escape the reaction vessel. Okay. First question, they want us to define the reaction rate. Oh, before I even go there, there's something significant I just forgot to highlight. The concentration of our acid is the same in both experiments. Are you together? As well as the mass of my magnesium. Are you together? Is the same. So both of those two things are my controlled variable in this investigation. However, there is an independent variable. Are you together? They have changed the states of division of our magnesium. In the first experiment, it's used as a ribbon. In the first experiment, is used as a solid, and in the second experiment, it is used as a powder. So that means they have changed the state of division of my magnesium, or rather they have increased the surface area of magnesium in experiment 2. Are you together? So our independent variable is basically the states of division of magnesium. Okay. And then now we are being asked to define reaction rate. Reaction rate, guys, is the change in the quantity of either reactants or products per unit time. Are you together? And obviously that quantity can be concentration, it can be the mass of both reactants or other products, it can be the number of moles as well. Are you together? So the change in quantity of reactants, or you can say the change in quantity of products over time, or just say per unit time. Now, okay, for this investigation, write down the independent variable. Since they have changed the state of division of my magnesium, it simply means that the state of division of magnesium is my independent variable. Or maybe I can prefer to say it like the surface area of magnesium is the independent variable. And then the controlled variable, the concentration of the acid is my controlled variable, as well as the mass of the magnesium is my controlled variable. Okay. Let me rewrite the reaction over there. I have magnesium solid plus hydrochloric acid giving us magnesium chloride plus hydrogen gas. And then I have a 2 there just to balance the equation. Okay, the change in mass of magnesium is calculated and recorded in 2 minutes intervals for both experiments. The results obtained are shown in the graph below. Obviously, this is not drawn to scale. Okay. Since guys in experiment 2 they have increased the surface area since now the magnesium is in powder form, it simply means that the reaction 2 will have a faster rate of reaction. In simple terms, reaction 2 will reach completion faster. Are you together? Since we were told that the acid is in excess, it simply means that magnesium is our limiting reagent. Are you together? And we know that in a chemical reaction, the limiting reagent will be used up completely. That's why as time progresses, the mass of magnesium will become 0 over there at the x-axis. Are you together? So for experiment 1, it takes 16 minutes for magnesium to be completely used up. For experiment 2, it takes 10 minutes for magnesium to be used up. Né? And it makes sense because in experiment 2, they've increased the surface area of our magnesium, and hence we will have more effective collisions, and that's why the reaction rate will be more faster. Okay, now let's answer the questions. Use the information on the graph. Firstly, they want us to calculate the volume of hydrogen produced in experiment 1 from t is equal to 2 minutes and t is equal to 10 minutes. Okay, I can simply use my magnesium to know how much hydrogen I have formed. Are you together? Why? Because magnesium is my limiting reagent. It will be used up completely. Okay, I can simply calculate the change in mass for my magnesium. Né? When t was equal to 2 minutes, the magnesium had a mass of 2.6, and then obviously it decreased over time. And then when t was equal to 10 minutes, the magnesium was simply 0.2 grams. So the difference over there will simply give me 2.4 grams. So this will be the change in magnesium. Basically, this will be the amount of magnesium which will be used to form hydrogen when between t is equal to 2 minutes and t is equal to 10 minutes. Né? So that's the amount of magnesium that will be used. So I can simply calculate the number of moles of the magnesium that will be used to form my hydrogen. I can simply say the number of moles that will be used is simply the mass of magnesium that will be used all over the relative atomic mass number. I know that 2.4 will be used between that time interval, and obviously the molecular mass or the relative atomic mass number for magnesium, it's 24. And then this will simply give me 2.4 divided by 24. I'll simply get a 0.1 mole. So I now know that 0.1 moles will be used to form hydrogen between this time interval. Now, okay, since guys the ratio over there is 1:1, it simply means that the number of moles of hydrogen that will be formed will be equal to the number, will be equal to the number of moles of magnesium that will be used. Are you together? So we'll simply have 0.01 mole. So I know that between this time interval, I will only form 0.1 mole of hydrogen. Okay. What do they want us to find? The volume. Okay. Since you are given the molar volume, guys, we are not supposed to use the one that is at the back of the question paper. So I know that the number of moles of any gas is equals to volume of that gas divided by the molar volume. That's 0.1 is equals to the volume divided by 25. So therefore, the volume of hydrogen is simply 0.1 multiplied by 25. 0.1 multiplied by 25. I'll simply get 2.5 cubic decimeters. So this is the amount of volume that was formed. Okay, let's go back from step number 1. Firstly, we calculated the change in mass of our magnesium, or we can say the total mass which was used. Let me say the total mass which was used, mass that was used. Initially it was 2.6 grams, and then finally the mass was 0.2 grams. So the difference between the two will simply give us the amount of mass of our magnesium that was used. All together. After finding the mass of the magnesium which was used, we then went and calculated the number of moles of the magnesium that were used. After finding the number of moles, we simply use the ratio and proportion to find the amount of hydrogen that will be formed by magnesium. All together. And since the ratio is just 1:1, I know that the number of magnesium that I will use will be equal to the number of moles of hydrogen that will be formed. All together. After finding the number of moles for hydrogen, I then use this formula over there to calculate the volume. All together. And then I got the volume of 2.5 cubic decimeters. Okay, 5.3.2. I'm being asked to calculate the initial mass of magnesium used in if the average rate of reaction formation of hydrogen in experiment 2 was 2.08 times 10 to the power 4 moles per second. Okay, the average rate of formation of hydrogen. I know that for me to form hydrogen, guys, I must use up my magnesium at all, because magnesium is my limiting reagent. Excuse me, all together. So the rate of formation of hydrogen will be the rate of decomposition of magnesium. All together. Why? Because this is 1:1. Are we together? Okay. I simply know that the rate of reaction for my hydrogen will simply give me 2.08 times 10 to the negative 4. This is in moles per second. This is my rate of reaction in moles per second. Okay, but what is rate of reaction, guys? Rate of reaction is basically the change in the number of moles divided by the time. All together. I was given the rate to be 2.08 times 10 to the negative 4, and then the number of moles final for my oxygen minus the number of moles initial for my oxygen all over the time. I know that experiment 2 took 10 minutes to finish up, but I was given the rate of reaction in seconds, so I must change the 10 minutes to be in seconds. So I'll simply say this will be 10 minutes multiplied by 60. Are you together? So 2.08 times 10 to the power negative 4 all multiplied by 10 times 60. Why am I doing this? I'm just cross multiplying. I'm trying to get rid of fractions. This will be 0.1248. This is the number of moles of my hydrogen final. But remember that, guys, initially I did not have hydrogen. Are you together? Why am I saying that? Because hydrogen is my product. When the reaction starts, there was no hydrogen formed. Hydrogen was formed because magnesium was used. Are you together? So initial number of moles for hydrogen, they were basically 0 moles. So I now know that the number of moles of my hydrogen that will be formed will basically be equal to 0.1248 moles. Let me write the SI unit. Are you together? But I know that since the ratio of hydrogen and magnesium is 1:1, it simply means that the number of moles for magnesium is the same as number of moles for hydrogen. that was formed. That's 0.1284. Are you scared? Remember that, guys, magnesium will be used up completely to form hydrogen. If this is the total number of moles for hydrogen that were formed, that means the total number of moles initially for my magnesium were these. Are you together? But what am I looking for? I'm looking for the initial mass. I know that number of moles is equal to mass all over the relative atomic mass number. That's 0.1248. I don't know the mass, but I know that the relative atomic mass number is just 24. So therefore the mass, I'll just cross multiply there. 0.1248 multiplied by 24 will simply give me a mass of 2.9952, which is basically equals to 3 grams. That's basically equals to 3 grams if you round off to 2 decimals. Né? Okay, so that's how, guys, we're supposed to calculate the initial mass. Let me take you back to the calculations. Né? We were given the rate of formation of our hydrogen gas. Are you together? We were told that the hydrogen gas was what's going on now? Excuse me about that, guys. Né? We're told that the rate of formation of hydrogen gas is equal to this one, né? But it is given in moles per second. That means for me to calculate the rate of reaction for hydrogen, I just needed to say the change in moles of my hydrogen all over unit time, né? And that's what I did over there. Change in moles is just the number of moles final minus the number of moles initially. But remember that initially there was no hydrogen formed. Hydrogen was formed because of the reaction between magnesium and hydrochloric acid. Are you together? So we had 0 number of moles for our hydrogen, and then we went and we went to calculate the number of moles of our hydrogen after the reaction has reached completion. We found that we got 0.1248, and since the ratio of between magnesium and hydrogen is just 1:1, it simply means that the number of moles of magnesium that will be completely used up is equal to the number of moles of hydrogen that will be formed. Are you together? After finding the number of moles for my magnesium, I went to the equation that say number of moles is equal to mass all over the relative atomic mass number, and then calculated the mass of my hydrogen, of my magnesium rather. Then I got 3 grams. Okay, use collision theory to explain why the curve of experiment 2 is steeper than that of experiment 1. The curve, guys, whenever you deal with reaction rates of reactions, né, the curve simply tells you about, or the steepness just tells you about the reaction rate. Are you together? The one which is more steep has a faster reaction rate. So we can see that experiment 2 has a steeper graph because it has a faster reaction rate. Né? And why is the reaction rate faster? Because they have increased the surface area of magnesium in experiment 2. Why am I saying that? Because remember that, guys, we were told that in experiment 2 our magnesium was in powder form. Are you together? So they've basically increased the surface area. So basically more particles will be correctly orientated now, and then we'll end up having more effective collisions, and that's why the rate of reaction will increase. So that's how, guys, you're supposed to tackle that question over there. So just stay tuned and wait for more videos. Thank you.